In this demo, we'll have a look at an acoustic data set where the calls were the individual detections and fit a model to it. First, we start out by looking at the data, the capture history, detectors, and mask, and then we fit a model to these data. So let's have a look at the data. These are data from an acoustic survey of frogs, which is available from the ASCR package. And the code on the left shows you how to bring that data into the workspace. The frog is the Western Cape moss frog, which lives on the Table Mountain above Cape Town in South Africa. And the data are called lightfooty after the species name of the frog. From this description, we can see that the data included here are only from a 25-second section of the recordings, but we'll see that the data include plenty of acoustic detections for us to analyze. We can have a look at the frog data using the structure function. That's a function you're already familiar with. The data object is called lightfooty. Again, we see a list of objects, and the first in the list is called bin capped, which is a data frame with 225 records, one for each call, and 6 columns, 1 column for each detector. The next object we need from this list are the detectors. Here the information is stored in the data frame traps with 6 records containing the coordinates of the detector locations. The last object we need is the mask, which is the grid of points across the study area from which frogs could have been heard. We had learned how to create all these objects in previous lectures, but in this case, they have been created for us already. We also have more information for each call besides the 3 objects pointed out already. Note there are 2 more data frames in here with information for the individual calls. One on signal strength called SS and one on the time of arrival called TOA. We're not going to use these during this demo and we'll ignore them for now. We can plot the mask and the traps to get an idea of the arrangement. So we use the plot function with the mask object as the input to plot the mask. We then use the points function to plot the locations of the detectors on top of the mask. Notice that I've used the argument PCH equals 19 to show the detector locations filled in as dots and the argument CX equals 2 to make them bigger compared to the mask dots. Let's have a look at the plot. So we know that the coordinates are always given in meters, so we know that they must have used a buffer of about 40 meters. And we can see that the microphones were arranged in this D-shaped configuration. In the first step, we extract the capture history from the data object. Otherwise, the functions are set up to use signal strength and time of arrival as well for model fitting. We fit the model with the ASCR function fit.ascr as before, but this time notice that I have specified a different argument. This is where you specify the function for your detection model. We've only looked at one model so far, the half-normal model with parameter sigma. This is the default model in ASCR, and if you leave this argument out, like we've done before, it will automatically use the half-normal function. I just wanted you to be aware that you have the option to change it here. We use the summary function to get the parameter estimates. First, the output tells us what detection model it used. We can see the half-normal model was used, which we asked for. And again, we're presented with estimates for the 3 model parameters, density, G0, and sigma. We can see that the estimate of G0 was 1, which means that all calls at the detector were detected with certainty. What I would like to point out, though, is the density estimate given here. Note that it is still called density here and not call density. ASCR does not know that we used calls instead of animals or group. You can also think of it as density of the detection units. And in this case, the detection unit was calls. Therefore, it is density of calls. Note also that the large number for this density estimate comes from that the unit is hectare, an area quite a bit larger than our study area. The time unit is the duration of the recording, that is 25 seconds. So the occasion was 25 seconds. This is a bit awkward perhaps to have a density estimate as given as per 25 seconds. We'll see in the next slide how we can turn this into a density estimate per minute. So we can convert the call density estimate into number of calls per hectare per minute by specifying the survey length in minutes. We do this with the argument of the fit.ascr function called survey length. In order to get a density estimate per minute, we need to specify the survey length in minutes. 25 seconds expressed as a fraction of a minute, or simply 25 divided by 60. So we run this model and obtain the following output. Notice that the detection model parameters G0 and sigma have not changed in comparison to before, but the density estimate has changed, and now the density estimate is call density expressed as the number of calls per hectare per minute. Here are some key points. We've expanded our knowledge about the fit.ascr function a little bit in this demo and have fitted an acoustic SCR model with calls as the detection unit. One of the things to remember is that when calls are the detection unit, the density estimate is given as calls per hectare per duration of the occasion. We can control the time units of the call density estimate with argument survey length.